welcome back. So, we were discussing the MG1 queue and we were on our way to deriving the PK formula, the Polacek engine formula, which gives us the expected waiting time in an MG1 queue, right. So, just recall that you have this MG1 queue, first come first serve, arrival process is Poisson of rate lambda, the expected let us just say service times VI are IID and independent of arrival process. Then so yeah, this is only for first come first serve service discipline. This want to calculate expected waiting time in the queue experienced by an arriving customer in steady state. What do we mean by steady state? Steady state means that the system has been running for a very long time, right. So, we want to calculate expected waiting time spent in the queue by an arriving customer as t grows large. Okay. So, the way we did this, so we had put down some equation if you remember. So, typically when there is an array, when an arrival is coming, there will be a one customer who is getting served and a bunch of customers who are waiting in queue, correct, and a particular job arrives at a time t, okay, as a part of the Poisson process. So, let WQT they say, I think I wrote it like that, right. WQT is the waiting time experienced by a customer arriving at time t, right, and I denote it by R of t as the residual service time of the customer in service. So, a customer arrives at time t, that customer would have to wait, right. How long would he have to wait? That customer has to first wait for the there is somebody who is already at the server, that person has to finish service, right. So, that residual time he has to wait and then he has to wait for the waiting times of all of these guys, right, who are already in front. So, remember we are doing first come first serve, right. So, you have to wait for all of this, right. So, the equation we wrote down in the previous lecture was that WQ of t is equal to R of t plus can you tell me sum over I is equal to 0 to NQ of t minus 1, is it? We can check this times. So, the sum of then you have that much to wait, is that correct? So, you have So, this is saying that you are waiting for the residual time plus NQ of t is what? So, let me just say what NQ of t is. Sorry, yeah. So, this is sorry LQ of t is the this is the LQ is the notation for the number of customers waiting in queue, right. Customers waiting in the queue at time t, right. So, this is the notation we use, right. So, I hope, right. Sum of service times of waiting customers. All right. So, now what do we want to find? We want to find expected WQ of t as t tends to infinity, right. Correct. This is the steady state waiting time experienced by an incoming customer. Okay. So, in doing this, we are going to invoke some key properties which we have studied before. Okay. One of them is pasta property, which is Poisson arrival C time average behavior, right. Remember, this time t is not any old time, it is not some generic t, it is a time at which what happens, this particular customer is coming into the system, right. So, a customer is arriving at time t, and that at time t the arriving customer sees a queue of LQT, right, and sees a residual time of R of t, correct. Now, in general, the residual time or the queue length seen by an incoming customer is not the same as the typical the time average behavior, right. The typical statistic seen by an external observer can be very different by the statistic seen by a arrival to the queue, right. We gave an example, if you remember last class, right. We took a GD1 queue, right, and in general for a GG1 queue it is not at all the case that the residual time and the queue length seen by an incoming arrival need not be the same as their corresponding time average values, right. But for an MG1 queue the arrivals are Poisson, right. So, what we will see is that these random variables at time t, this RT, right, which is the residual time, and this LQT will follow time average statistics, okay, and that is because of pasta property. The reason is that we are starting time at an instant when the first arrival the arrival comes at 0. The question is, why are you starting at V0, right, in that equation. If you remember, we are considering time t equal to 0, time starts ticking when the first arrival comes, whose file size is V naught, okay. It is just a matter of notation, we have been following this notation, but it does not really matter, right, it is okay. Anyway, what you want is you want pasta here, and then you want to be able to invoke these renewal reward type results for calculating R of t. Due to pasta, the incoming arrival at time t sees residual times and queue length which are statistically same as those seen by an external observer. Now, as regards R of t residual time, how does the residual time behave? Right. So, at time 0 a particular customer gets into service, right. Let us say the first this is I am going to plot, what am I plotting? I am plotting R of t against time, right. So, what is the time average behavior of R of t? R of t is the remaining service time of the job in service, of the customer in service, correct. So, the first job has the customer who comes at time 0 has V 0 to begin with, right, and then he is being eaten away at a constant rate, correct. So, you will get this sort of an isosceles triangle, right, whose height is V naught and this is V naught, correct. I am just plotting the residual time left at the server, and then there will be a V 1, right, it suddenly jumps again starts getting eaten, right, at a constant rate, correct. And then there is a V 2, it is probably quite large, and there may be a small V 3 and so on, right. And then let us say the system becomes empty, okay. It just might, right, I mean in you can draw a trajectory, and then residual time is, so this let us say system empties. I am just drawing some typical R of t sample path, okay. Then it is 0 for some time until the next arrival comes, right, which will again have these triangles, right. These have to be isosceles triangles, okay. This is a plot of the remaining. So, how much residual time does the job and service have left, you know how long is it going to be at the server at time t, right. Is that clear? And of course, when there is nobody in service, R of t is 0, right, which is what I have plotted here, R of t is 0 out here, okay. Clear? So, this is a renewal duration, you know that, right. So, from 0 to the first arrival to a empty queue is a renewal duration, and R of t constitutes a renewal reward process for this renewal for this underlying renewal process, correct. So, what we would expect the following, right, you would expect what is this limit t tends to infinity R of tau d tau, which should ideally by ergodicity you would expect ergodicity you would expect is the same as the ensemble average reward, right. is equal to expected reward over one renewal interval over expected let us call this S1R or whatever, right, this let us say is X1R, right, the first renewal expected X1R, right. Correct. So, you have to look at what is the total area under all these triangles, right, divided by what is the expected renewal duration, right. You can calculate it like we did for you can calculate it directly also, okay. But there is also a you can try go ahead and do this, okay. We already know, I think from our homework problems, what is the duration of these busy periods and idle periods. After all, what is the expected duration of the idle period here? How long is this guy? This guy is equal to, yeah. So, this is an exponential with parameter lambda, right, exponential with mean 1 over lambda, correct. And what is the fraction of the time that the server is empty? Lambda times expected V or lambda over mu is the fraction of time it is busy, correct. So, we can easily find the expected time of this busy periods. Expected idle periods are of course 1 by lambda. So, we can find the expected x 1 r easily, and of course, you can find the numerator expected r 1 by just adding up the areas of these isosceles triangles, okay. Another way to directly write this down, okay, is by again using Little's law, okay. You can see with probability 1 minus lambda expectation of V, the system is empty, right, and with probability lambda expectation of V, there is somebody at the server, correct. So, when there is nobody at the server, R of t is 0. When there is somebody at the server, what is expected R of t? You would, so I am trying to see, I am trying to guess, you can do this calculation, right, expected R 1 over expected x 1 r, you can easily calculate by adding up all the isosceles triangles, but I am just trying to be telling you a different way of calculating this. So, R of t is, so after a long time t, right, I am looking at R of t, expected R of t after a long time, right. So, this should be equal to, with probability 1 minus lambda expectation of V, which is my load on the system lambda over mu, it is 0, R of t is 0, right, and with probability lambda expectation of V, my expected R of t is what? It is expected V squared second moment of the service time over 2 expected V, right. So, what does this work out to be? This works out to lambda expectation of V square over, this cancels, right, over 2. Okay. So, you can I have made this intuitive calculation, but you can check that this answer comes out even if you just calculate the sum of all these areas, the expected reward over an renewal interval and divided by expected x 1 r, expected x 1 r you can calculate, right, we know the busy period durations, correct. You can please verify this, okay, clear. See, I am making heavy use of pasta property here, because the expected residual time seen by an incoming arrival, I am equating it to the time average residual time, which I am again saying is equal to ensemble average residual time, right. This is by renewal reward, okay. You can calculate this ratio directly. I am just making a Little's law trick here, right. Correct. Basically, Little's law trick meaning I am looking at the Little's law for server, right. Little's law trick for server. Okay. So, this is another way to calculate things. Good. So, we know expected, so we have this term, right. So, in this equation I want expected W q of t, which is this guy, right. I have expected R of t as t tends to infinity, right. I just have to figure out what this the second term is. So, I will write, so go back to that equation. So, expected WQ of t limit this is what I want, correct, is equal to limit t tending to infinity expected r of t plus limit t tending to infinity expectation of the sum I is equal to 0 to, this is the notation, right, LQT minus 1 Vi, correct. So, the first term I know, which I just calculated, it is lambda expectation of V square over 2, correct, plus what is this? Now, this is a sum of the Vi random variables, right. How many of these Vi random variables am I summing? I am summing another random number of these random variables. Okay. Now, LQ of t, right, is the number of people waiting in the queue, right, at time t. This LQ of t, number of people waiting in the queue, depends only on the past arrival times and the past departure times, right. So, it depends on the arrival times of customers who come so far and the departure times of customers who have already left, right. In other words, the number of people who are waiting in the system at this time t LQT, right, is actually independent of the service times of the people who have not even entered service, who they have come to the system, correct. These VIs are the service times of customers who are waiting, but the LQ of t is only a function of arrivals which have come in the past and the service times of the customers who have already left, right, which are again independent of the VIs of the customers who are waiting in queue, right. So, this is a random sum of random number of random variables being summed, where this LQT, the number of random variables you are summing, is independent of the VIs, the number, right. So, this is like this is not even walled, this is even simpler than walled, right. I mean, this is a trivial case of walled if you like, where the number of terms you are summing is independent of the Xi's, or in this case VIs, right. So, LQ, the issue is that LQ LQ, I guess LQT is independent of VIs for I is equal to 0 to LQT right. So, using that I can write this as limit t tends to infinity expected V times expected LQT, correct, because if you are summing an independent, if you are summing a number of random variables where the number of random variables is independent of the random variables you are summing, you get product of the expectations, right. This is like a very simple version of walled, now even walled is not necessary, right. Okay. So, now what is expected LQT? It is the queue occupancy after in steady state queue occupancy seen by an incoming arrival. By pasta, LQ of t is also has the same distribution as the time average queue occupancy, right, correct. Again, so again, so take this remark here, right, due to pasta, right, because of this remark expected LQT seen by an incoming person arrival the same as the time average queue occupancy, right. So, this can be written as lambda expected v square over 2, the first term is the same, plus v, this is expected v, which is times LQ bar, right. What is now LQ bar? See, LQ bar is the, this is by pasta, right. See, what I am saying, expected LQT, which is the expected occupancy seen by an incoming arrival, is same as the time average Q occupancy, that is pasta, right. Now, what is LQ bar? We already know. See, what do we want to calculate? The average waiting time in the queue, right. So, can I not write, so let me call this WQ bar, right. It is the same as, if you believe that time averages and ensemble averages can be interchanged, this is just what, sorry, this is plus expectation of V times lambda WQ bar. How is this? This is by little, correct, with me, which means WQ bar is equal to what? Can you help me with this? Lambda expectation of V square by twice 1 minus okay. I know the answer, this is what it will come out to be, right, if you rearrange it. So, this is the famous PK formula, I wrote it down so confidently because this is a standard formula, right. You will just rearrange the above equation, you get this. This is called PK formula. I am going to spell this incorrectly, I think. So, Polacek, I think this is it, Polacek Khinjin. Okay. This is the famous Polacek Khinjin formula for the average waiting time in an MG1 queue. Okay. This is only for FCFS. Okay. If the service discipline is different, you cannot use this formula, okay, because we have very crucially used the fact that you are waiting for, if you look at this picture, right, you are waiting for the person in service and then waiting for everybody who has arrived before you, right. So, this is very, we are directly using the FCFS nature of service, otherwise this formula will not hold. So, the key intuition, so what is the most striking thing about this formula? The expected waiting time in queue is proportional to the second moment of the service time, okay. What is the intuition? The intuition is that, see, suppose see these VIs are IID, right. So, some are small and some are big. The way I have lost, the way I have drawn it, for example, I have drawn some small triangles and big triangles, right. So, typically when you have a scenario like this with all these isosceles triangles, you tell me this, right. The arrival process is a Poisson process, which is uniform at coming at a rate lambda. So, if you draw the arrival process, more arrivals are going to come here, right, and very few arrivals are going to come during smaller service times, right. So, when a particularly large customer or a large file is being served, you will have a lot of customers coming, correct, and they will all be held up by this very large file, very large customer, right. See, this is just like if you are showing up to a bus stop buses are a renewal process, right, you are arriving at a bus stop according to a renewal process, you are more likely to show up when the duration between in 2 bus arrivals is very long. This is a bit like that, right. So, typically the incoming pause on arrival comes in when there is a very large file in service, right. So, you can view this as this mice and elephants, you know, typically the files are of some average size, but when a particular pause on arrival comes into a queue, the file in service at the server, the customer in service is an elephant, right. The residual time is proportional to the second moment, right, of the service time. Okay. So, expected V square can be very large compared to expected V, right. Second moment could be can be made arbitrarily large for a given expected V, right, that is possible. So, in that sort of a scenario you will have this FCFS MG1 queue will have the customers coming in will face very large expected delays. Okay. Of course, for a MM1 queue what happens? The residual service time of the customer in service will also be exponential because the file sizes are exponential with some parameter mu, right. So, you can check that I mean you can verify PK formula for the specific case of MM1 queue and you will get a simple formula for MM1 queue. Okay. Anyway, so this is WQ bar which is the expected waiting time in the queue, and WQ which is just the let us say W bar, right, which is the average system time will be WQ bar plus how much? That customer service time, right. So, this will just be again lambda expected V square over twice 1 minus plus expected V. Okay. And from here can you calculate L bar and LQ bar can also be calculated, right. L bar will simply be lambda W bar by little and LQ bar will simply be lambda WQ bar. So, all this can be calculated for MG1Q. Okay. So, we are assuming that expected V square is finite, the second moment is finite.